All right. Good day, everyone. Today we will be discussing our new topic, and that is all about earthquakes. So, before we start the proper discussion, I want you to observe and watch this video. Okay? So, let's now watch.
And in 2001, Indonesia is still leading, followed by Papua New Guinea and Japan. So we're almost done.
So, let's go back to see on which is the country that has the most earthquakes. Okay? So, in 2009, 19 rather, Indonesia garnered the first place. So, it has 852 earthquakes that had happened on the last century, followed by Papua New Guinea, Japan, Chile, the Aleutian Islands. Six is our country. We have the Philippines, Russia, Mexico, Japan, and China. And with this data, we can determine that almost all of the earthquakes that had happened in our planet is located on the region on the Pacific. Okay, so basically the Pacific Ring of Fire, right? So we can almost say that these earthquakes happens on the plate boundaries. Okay, so the boundaries on which um, two plates are connected. Okay, and these boundaries are the ones, the locations, that there is movement, and if there is movement, there are tremors, and if there are tremors, there will be earthquakes. Okay, so again, the top one is Indonesia. So let's go now to the to our country. So we have the Philippines. So as an overview, we have the different fault lines. Okay, the major fault lines here in our country. So we have the fault lines. We have the number one, the Central Philippine Fault. That is the areas that is affected are the entire Ilocos Norte and going down to Davao del Norte. Second of which, we have the Marikina Valley Fault. So this comprises the whole Marikina ridge system. So from Montalban going to the southwest to Oriental Mindoro. Thirdly is we have the Western Philippine Fault. So it consists of the west part of our country. So from the Luzon Sea to the Sulu Sea. Okay, on the west portion. And next, we have the Eastern Philippine Fault that is located mainly on the Philippine Sea, the east portion of our country. And lastly, we have the Southern Mindanao Fault that is located on the Moro Gulf and Celebes Sea that is located south on our country. So let's take a look from the map. So here's the map of the active faults and trenches in the Philippines. So we have the trench here. This is the Manila Trench. And this is the Negros Trench here. And the Sulu Trench. So as you can see that the whole system here is created by series of trenches. And on the east side, we have the East Luzon and the Philippine Trench that's located almost on the entire vicinity of the east side of our country. So on which we can see from the last topic, the plate tectonics, that on this area we have the Eurasian plate that has the boundary from the trenches. We have the Manila Trench, the Negros, and the Sulu. On the east side, we have the Philippine Trench, and the plate that is located here is the Philippine Plate. And on the southern portion, we have the what? We have the Cotabato Trench. That is the boundary between the whole Philippine system and the Sunda Plate that is located below on the south portion. Okay? So, the Philippines is encompassed by three different plate systems. And the country is also considered as a one small plate. That is called the microplate, the Philippine Mobile Belt. And here we can see different fault lines. Okay? The one that I have discussed recently. So, we have these five uh, different major fault systems. And these are the five major fault systems. The one of which that is the most famous is this Philippine Fault Zone here. So that is located in the Ilocos Norte region, going southeast until to the Davao region. Okay, so let's try to look it on a seismic map. So here we can determine the earthquakes that had happened on the year 1968 to 2018. And the major earthquakes or the most earthquake that had happened from this timeline is located mainly on the east southeast portion of the Philippines. And also with this area here. Okay? So this is the Marikina fault system here. And this is the east east what you call that? So the Eastern Philippine Fault that is located here, and also with the south portion. So we can actually determine on which places that has the most earthquakes every now and then, and we are actually experiencing it. Okay, now Let's take a look on another map. So here we can see the major earthquakes that had happened on this the same timeline. So we can see that it had happened here, the magnitude 7 plus earthquakes on here in Cebu and here in the Pagadian region. So there are actually small and minor earthquakes that we cannot actually feel. So most of it happened on the trenches itself. So especially in the Philippine trench. So every now and then we are actually experiencing tremors, but we can actually feel it because it is located underwater and deep on the earth surface. Okay? So with this, we have the our topic today. It's all about earthquakes. So by definition, earthquakes are the shaking of the earth that is caused by the release of energy from built up stress. Right? So, what causes the buildup of stress? Okay, what is the reason on which these areas or this location has tremors that is happening every now and then? Okay, and that is because of the movement and deformation of the Earth's crust. So there is movement from the discussion before that I have told you. From the plate tectonics, we have the continental drift. And these continents are actually moving and actually drifting, making it in such that it will deform the structure that is located below the surface of the Earth. Okay? And we have the two types of earthquake generators. Okay, one of which we have discussed eh, in the last session. So one is we have the plate boundaries or what we call tectonic boundaries. And the second one is we have the different fault systems. Okay. Now, what is a fault? Okay. What are faults? So, faults are actually weaknesses or the weakness zones in rocks on where movement may occur. Okay, so we have what we call two different types of faults. One is we have the active faults. The second one is we have the inactive faults. The active faults are the ones that has history of the movement. The inactive ones do not have history on it. Okay, so again, this is the location on which earthquake may happen because the zones of which are very weak that it cannot withstand stress. Okay, so another definition of a fault. It is a surface or narrow zone in the Earth's crust which one side has moved relative to the other side in a direction parallel to the surface zone. Okay, say for example, we have these pictures here. Okay, so we have two structures or two, shall I say, two layers. So we have this fault line here, and this is the hanging wall block and the foot wall block. So the hanging wall block is the one that is located above the fault line, and the foot wall, from the word foot, it is located below the fault line. So these two structures here are moving parallel to each other, making it such that it will deform like this on the second picture, and it will uh, what you call this? It will it will break rather on the second picture, and it will deform on the third picture. Okay, so we can see that I have these blocks here. So this is the fault line, this one, okay, and the middle portion. If we move this one, so we can actually say that this area here on the middle portion, this will break because each of these rocks that is located here has its own limit or what we call strength, that maybe it can surpass it or either it will flow on it. So there are two uh, uh, outputs. Okay, it may flow or it may fracture. So we have two types of deformation. This picture here is what we call brittle deformation. So we can see that if and only if that this portion of blocks here will deform uh, in a brittle manner, these sections here in the middle will break. Unlike on the third picture, if it undergoes ductile formation, it will just what? it will just flow, or what we call, it will produce bending. So the factors of which that will influence the strength of a rock and how it will deform includes temperature, confining pressure, the rock type, and also time. Time is one factor that can determine that because it does not happen uh, uh, in a timely manner. We cannot actually predict on when will it be moving. Okay? So there are three fundamental kinds of stress to which these rocks are subjected below the earth. One, we have compressional. Second, we have tensional. And the third one is we have shear stress. So what can we see from these three fundamental stress is that it is moving prior to its own direction. So we have the tensional stress, making it that it is being stretched away from each other. So if we can have an example, if we have a rubber band, if we stretch it, making it that the pressure will go on the sides. Unlike in the compressional stress, the pressure is located inside, okay, or in the middle section. Okay, the pressure is on that direction. Shear stress, on the other hand, travels both location or both directions. So compression, again, it will become compressed. The pressure will go inside. Tensional, the pressure is going outside. And shear stress is basically on either sides. All right. So let's recall the different fault blocks. So we have the hanging wall block and we have the footwall block. So the hanging wall block is the fault block that is above the fault line. The footwall, on the other hand, is located below the fault line. Okay? So in here, from the differentiation of hanging wall and the footwall, we can determine on what type of fault that is in the area. Because we have three types of faults. Alright? So we have the reverse fault, the normal fault, and the strike slip fault. So reverse fault, okay, in this image is we have the fault line here, all right? So the hanging wall block is located where? On which block? This is the hanging wall block. And this is the what? The foot wall block. So in this area, we can determine that like this, the hanging wall block is what? Is going upwards. Okay, the hanging wall block is going upwards and that resembles the reverse fault. Okay, and we have the normal fault. Normal fault, same inclination. The hanging wall block is located in this block here. The footwall is in here. So, in which blocks does the hanging wall block is moving? Is it on the upper direction or in the south direction? So, it is moving below the footwall block. And that resembles normal fault. Strike slip fault, on the other hand, is different from the reverse and the normal fault because it is moving away from each other. The two blocks are moving away from each other. So that resembles a strike slip fault. Okay? And there is what we call a thrust fault. It is a kind of reverse fault, same with this one, but it has a small dip angle. So in a reverse fault, we can actually determine if it is a reverse one or if it is a thrust fault by based on its angle here. So if you have a high angle, that will actually resemble a reverse fault. But if it is, this is the reverse fault. The thrust fault looks like this one. The inclination is the inclination angle is much lower or lesser than that of the reverse fault. Okay? So these are the three main types of fault systems. Okay, on which each of these fault types has its own as underlying stress motions. So in normal fault, um, it is experiencing an extensional stress or the tensional stress. because the area on which is being stretched, making it that the whole portion in the middle will go downwards. That is why the hanging wall block here goes below the footwall block here. Unlike with the thrust fault, it is being compressed via compressional stress. So there will be shortening and thickening of the area in the middle, making it such that the hanging wall will go upwards from the footwall block. The third one is we have strike slip fault, and that resembles a shear stress motion because it is only what you call this, it only moves parallel from each other. So these are the different kinds of differentiation. Okay, again, as we recall, normal fault is equal to what? Tensional stress. Thrust fault is equal to compressional stress. Strike slip fault is equal to shear stress. Alright? So now we will go to another orientation. Okay? By relative displacement or according to the slip of the fault. Okay? So we have three types of fault systems according to its slip. So one is a deep slip fault. So deep slip fault are those having tensional stress and compressional stress. So again, what are these fault systems that I've discussed before? So these are the normal and what? The reverse fault. So making it that the deep slip fault is dipping, only dipping. Okay, movement is parallel to its fault line. Strike slip fault are the ones that is approximately horizontal and is parallel to the strike of the fault surface, meaning it undergoes shearing. And these strike slip fault are what? The transform faults that is located in transform boundaries. Oblique slip faults is rather inclined obliquely on the first surface. So it is a combination between this tensional and compression stress and shearing stress. So let's try to visualize the movements according to a plane surface. So this is the movement of the strike, oblique, and dip. Strike slip is movement is horizontal on this plane surface here. Dip slip is going on the inclination itself. Oblique slip is moving inclined to both strike and dip motions. Or shall I say on the middle portion. Okay? So this is the orientation on which these fault types are moving on its different characteristics. Okay? So let's try to have a look at this one. Say, okay, normal fault is looks like this one. The hanging wall block is what? Going downwards. And the footwall remains. Reverse fault is that the footwall remains and the hanging wall block is located above the footwall. So this is the thrust fault. It has a lesser angle compared to the reverse fault. Okay? And each of these fault here has its own features because if we can see a fault scrap here, we have this fault scrap here or the remnants of the footwall because it has layers on it that will determine that this type of fault is a normal fault. And if you can see a overhang or rubbles of rocks, that will resemble a reverse fault or a thrust fault. So like for example, we have this one. What is this? So this is a what? This is a overhang. So we can see structures of rocks that is made from the remnants of a what fault? A reverse fault. This one, we can see that the layers here are being uprooted upwards. So this is what we call a fault scrap. So we can see that if we can observe on an area that it has this one, this area here has a normal fault type. This one, what type is this? What type of fault is this? So this is the fault line here. Alright, so which one is the footwall? This is the footwall and this is the hanging wall. Okay, from its orientation, from the orientation of the hanging wall moved upward or moved downward. So the hanging wall is moving upward. Thus, this is a reverse fault. This one. So this is the fault line, this is the footwall, and this is the hanging wall. The hanging wall is what? The movement is going up or going down. It is still going up because this one should be the same layer on this one. So the movement is going up. Therefore, this is a what? A normal or reverse. So again, let's try to this. So this is a reverse fault because the hanging wall goes upward. So this one, is it the same with this one? Very good. This is the same with this one. So meaning this is a reverse fault. How about this one? Where is the fault line? The fault line is on this portion here. And if this is the fault line, this is the foot wall and this is the hanging wall. And the hanging wall is located on which direction? Or the movement is what? Is it a it is it move or it has moved downward or upward? So basically, this wall here, this hanging wall moves downward and thus making it a normal fault. Another picture, we have this one. So this is the fault line. Okay? This section here, this layer here should be the same as here. So this is the fault line, this is the foot wall, and this is the hanging wall. Making it that the hanging wall moves downward in orientation with the foot wall. So this is a what type of fault? This is a normal fault. How about this one? So from the three main types of fault. So the movement of which is not inclined but on a horizontal manner. So therefore this is a strike slip fault. How about this one? Here we can see different fault lines. One is located here, second is located here, and other is this and this one. So from this area, okay, from this fault line, this is the foot wall and this is the hanging wall. Okay, from the orientation, the hanging wall moves upward or downward. So it moves downward. So therefore, this is a normal fault. How about this one? This fault line here. So this is the inclination. This is the foot wall and this is the hanging wall. The hanging wall moves downward or upward. Still, it is moving downward. Okay? So therefore, it is still a normal fault. How about this one here? Okay? This is the fault line. And this is the hanging wall. And this is the foot wall. Okay? So if this is the fault line, the hanging wall is what? Moving upward. So this is a reverse fault. So in this picture, we can actually see two different types of fault. So maybe the whole section of rock here is very brittle and it does not have the strength that can withstand the pressure or the movement on the area itself. Okay? So next, let's talk about the different types of fault according to its shear sense. So shear sense, it talks about strike slip faults. And strike slip faults have two different classifications. We have the right lateral or dextral and left lateral or sinistral. Right lateral is the one that is moving to the right portion of the block. Left lateral is simply saying the fault block is moving on the left portion. Okay? Say for example, this one. If you are standing here and you can see this block of structure here, so it is moving on the left side and that is automatically a left lateral strike slip fault. Okay? So based on the orientation of the observer on the next block that is located on the uh, uh, in front of the observer. So how about this one? So we have the word lane here, and we have the fault line here. So the movement of which, if you are here, if you are observing here, this is the fault block, the fault orientation. And this fault here is moving on what direction? Is it on the right or is it on the left corner? So it is moving on the right area. So this is what we called a right lateral strike slip fault. How about this one? Okay, if you are standing here and you are observing the block here, is it moving on the left or is it moving on the right? So we can determine it on this section here that this area should have been here. So the movement is going to the right. So therefore, this is a right lateral strike slip fault. Another picture, this one. So we have series of breakage here. So this is a uh, brittle structure. So here we can see several fault lines because of the brittleness. So the movement of which is, we can say that it is moving on the left side. So this is a left lateral strike slip fault system. How about this one? So this is a farmland. So this is the fault line here. So here we can see that it is moving, this block here, if we are observing on this area, this block here is moving on the left portion. Okay, is it left or is it left or is it right? Okay, it is moving on the left portion. So this is what we called a left lateral strike slip fault. Next picture, this one, moving to the left or moving to the right. So here we can see that it is moving to the right. So therefore, this is a right lateral strike slip fault. Last one, we have this. The road here should have been here. And this is the fault line here. Making it that this block here, this block of area is moving to the right. So therefore, this is a right lateral strike slip fault. Okay? So it is easy to determine if ever it is going to the left or is it going to the right. Just base it on its orientation of movement. Okay? So now next, we'll talk about an oblique slip fault. So oblique slip fault is a combination between the uh, deep slip and the strike slip. So it is moving obliquely from the original position here. So so we can see that it is moving here from here. So obliquely, on an oblique manner. And also with the strike slip fault type, we have also two types of classification of this oblique slip fault. So it is either a sinistral normal or a sinistral reverse. It is based on what? On the direction. If either it is going on a normal oblique or a reverse oblique motion. So sinistral normal is that we have the fault line here. Okay? Fault line. And this is the hanging wall and this is the foot wall. Okay, from based on its orientation, it's moving obliquely. But is it normal or is it reverse? The hanging wall is going upward or downward? It is going downward. So thus it is a sinistral normal. How about this one? This is the fault line. This is the hanging wall and this is the foot wall. The hanging wall is going upward but on a oblique manner. Thus it is a sinistral reverse. Okay? I have one example here so that we can actually visualize what is this sinistral fault system. So this one. This is moving on an oblique manner. But where is the fault line? This is the fault line. So therefore, this is the foot wall and this is the hanging wall. From which direction is the hanging wall moving? Upward or downward? It is moving downward. So therefore, this fault system here is obliquely moving on a normal manner. So this is a what? From here, this is a sinistral normal fault. Okay? So the last fault type, we have what we call rotational or scissor fault. So this is mainly that a fault system that slip changes rapidly with horizontal distance along the fault. So it mainly rotates. So like this one, I have this one. So it is rotating. This is the area direction. Okay, it's moving like this one. Okay, it is rotating. So like a seesaw, it has a fulcrum on this fault line here. So this is what we call a rotational fault. And it the features of it, if this will happen on a surface, the area should look like this. So it moves, or the feature should have a brittle manner. And the compression is as can visibly seen on this area here. Okay? So another. So these are the fault that is according to attitude. Okay? According to angle of the fault surface. So we can easily determine this by telling if that this fault has a fault angle that is more than 445, that resembles the high angle. But if it is less than 45 degrees, it is considered a low angle. Okay, this one. This is the fault line and this is the angle. So here we can see that this is a high angle fault. This one, we have the fault line here, okay, that crosses from this portion up to here. So by measurement with this angle here, this will be considered a low angle fault system. Question: can an area will have two fault? One is a high angle and one is a low angle. Yes or no? What do you think? Okay? So let's try to look at this picture. Okay. So mainly it can have a different angle system. So from this picture here, we have a high angle fault here and we have one low angle fault here. Okay? So if we have a high angle fault and if we have a low angle fault, there will still be a what we call vertical fault. Okay, so vertical fault mainly resembles a 90-degree angle on the fault line. Okay, so those were the types of fault uh, systems. Okay, in which earthquakes will happen. Okay, so now we will try to determine on what features can we look so that we can see that that area has a fault line on that, so that we can actually see and prevent if if ever there will be earthquakes that will happen, so that we can actually prepare. So we can recognize faults by these different features. Okay, one of which is we have horse fault slices. So horse fault slices are the ones that's located in the map that has brittle structures or compressional structures because of movements. So like this one. Okay? So this is a typical horsetail structure that this is the fault line. So it runs on a right lateral. So this is a dextral strike slip fault. And with this movement here, we have series of movements on this portion. And because of this area here that is moving on this portion here, it can have series of foldings. And this is what we call a horsetail structure. Okay? By image, it looks like this one. So this is a horsetail structure, making it that this area has a what? A strike slip fault system. So on a larger view, okay, this is a horse tail structure. So it is a bigger and a larger one. So therefore, we can see that this area here has a strike slip fault system. Okay. So another one, so that we can determine if the area has a fault line, is when we actually drill the area. Okay? So from this figure here, if we drill on such area that from a drill hole here, and if we can drill on another section here, so meaning there is a repetition of strata. So therefore we can see that we can observe this drill portion here, that it has a repetition on this 1 and 2 3 layers, so making it that the area is moving, that it has the same, so making it that this area here has a fault line. So if it is being repeated, there is what we call also an omitted version. Okay, so if there is an omission of strata, if we drill something on that area, that we can actually determine that. So if this one here, we can have the number 2 layer, and this one if we can have another 2 layer. But on the middle portion, it is gone. The second layer is uh, omitted. So therefore, we have a fault line here. And if the strata is being repeated, it means that the fault structure here, or the fault type is what? Is a reverse or a normal. So this is a reverse fault system. So repetition equals reverse fault. Omission is simply saying that this is a normal fault. Okay? Understood? So next, we have another structure. So if you can see a drag fault, meaning that the area is what? Has a fault line. Okay? So making it that the area is has been deformed all throughout because there is a fault line there, there is movement. Okay? Next, we have cut-off lines. So here, we can see that this is a fault scrap. And if we can see sedimentary layers on this portion that we cannot see on this other side, meaning that this section here, the boundary between the two, okay, meaning that it has a cut-off line, this therefore, the area has a fault system. And next one, rollover anticlines. So meaning that the area here, the block here should have been what? Should have been connected to this area. But it rollovers to this section here. That is because there is a normal or a reverse fault. This is a normal fault. Okay? So, again, we have fault scarps that will determine if the area has fault systems on it. And it has features that is characterized by sharp, increasing in a topographic slope. So, this is the making of the fault scrap. Okay? So, this one, we can actually see series of fault scrap here. And we can mostly observe it on a river system. This one is one famous fault scarps that is located in Iceland. Here is the fault scarp here. So we can see that what? This area here should have been connected with this area here. It must be plainly horizontal. So another physiographical criteria is that if we can see a ridge, a valley that is being offsetted. So offset meaning it goes from this section, it must have been connected to this area here. So therefore, it must have a what type of fault? A strike slip fault. And this strike slip fault here is right lateral or left lateral. This is a right lateral. This one, this is also a right lateral, that this river here should have been connected to this river section here. So therefore, this block here is moving to the right orientation of this block here. This one, okay? So we can see that the railroad is or has is bending towards to the right portion of this orientation block here. So therefore, the fault line is, di ba? We can see it here that this block here is moving to the right section. So meaning this is a right lateral strike slip fault. Okay? So all of those things that have been discussed is the orientations and the structures and the features of fault systems and fault types. Now we will discuss the fold systems. Okay? Folds. It is a distortion of a volume of material that manifests itself as a band or nest of bands in linear or planar elements within the material. So it is like a bended structure or a rock structure or of a massive structure that has been bended because of movement. Okay? So we have the geometry of folds here. So if one area, like for example, if I have a paper, this one, and if I compress it, it will fold. And this is the geometry of this fold. So we have this, the inflection point, the axial trace, the hinge point, the axial surface, the limbs here, and the hinge line is located on the axial surface. The hinge zone is located here, and the inflection line again is here. The amplitude is mainly, we can determine it, we can calculate it. That is in the mid portion of the limbs and going to the section here on this interlimbed angle. So if we can visualize it, it looks like this one. So this is the axial plane, this is the limb, and this is the whole structure here is the fold. Okay, so there is a fold system here. The structure should have been flat. Okay, the structure should have been flat, but because of movement, that is, the movement is going inwards, it is compressing, meaning that the area here is has become folded. And we have here the orientation. So this, we have the different types of orientation according to how is it being folded. So one, this is folded upright. So the axial surface is 90 degrees. We have inclined. The axial surface is basically inclined. Overturned is basically it has lower angle than the inclined. And recumbent, that has a inclination of 0 degrees. Okay? So again, upright 90 degrees, inclined 45 degrees, overturned less than 45, and recumbent 0 degrees. Okay, let's try to look at this figure here. What type of orientation is this? So we can see the fold here. And the actual surface should have been here. So the degrees is 90 degrees. So therefore, this is a upright upright fold. How about this one? This is the fold here. This is the inclination. So this must be a 45-degree inclination. So therefore, this is a inclined fold. Okay? How about this one? This is the orientation here. This is the fold. This is the axial surface. So meaning it has a 45, barely 45 degrees. So still, this is a what? This is a inclined fold. Right? So next, according to the direction of the facing of the fold. So we have an anticline and we have a syncline. Okay, from the word syncline, the fold is sinking. Anticline is the fold is going upward. So we have this series of folds here, meaning that if the axial orientation, if the fold is going upward, that is an anticline. If it is going downward, that is a syncline. Okay? So let's try to have this picture again. We have series of folds. On which part of this image is a anticline? So anticline, the section is, the movement is, orientation is going upward. So this one is the anticline. This one from here to here is the syncline. Okay? How about this one? This one is the orientation. It moves upward. So therefore, this is an anticline. This one. So this fold here is 0 degrees. Okay? 0 degrees. So but we can actually see if it is an anticline or a syncline because the movement is going upward. This is an anticline. And these orientations, the anti-incline and syncline, has its different features according to its style of fold of surface. So we have anti-forms and we have the syn forms. Okay, we can actually see this every now and then if we travel across provinces. So we have in anti-forms, we can see domes, whale back, and saddle. Syn forms or the syncline formations, we have basin, we have canoe, and we have shoehorn. Okay, let's look at some examples. This one, we have the orientation here. The fold is here. And it looks like what? Syn form. So this is a canoe. Okay, canoe. This one, this is the orientation here. So this is a syncline or anticline. This is an anticline. So therefore, what form is this? This is a whale back. This is a whale back. In maps also, we can determine if that area is a basin or a dome. So if you can see a dome, it looks like this one. So mainly we can see that this is a bulging surface. And if you have a hollow surface, that resembles a basin. Okay? This is a basin. And this is a dome area. Okay? From another map, we can see that these are the red ones, meaning this is the higher altitude and this is the lower latitude. So we can see that this section here looks like a basin. Okay? This is a basin, and this is a dome structure. Okay, now, folds under symmetry. So these folds are classified into two types again. It is either a symmetrical or asymmetrical. So symmetrical folds is that when one limb of a fold is the mirror version or a mirror image of the other one. So therefore, it has uh, equal structures. A symmetrical fold, on the other hand, does not have an equal image. So this one. So we can see that it has the same area. It has the same orientation. So therefore, this is a symmetrical fold. This one. So from here to here, this is a symmetrical. But if we consider the whole, this is an asymmetrical fold. Okay? So this sums up the fold system. So we have the fold types and the fold types. Now let's go to the earthquake basics. Okay, earthquakes. Again, these are tremors because of movements that is happening on fault lines or in the plate boundaries. That includes features like faults. Okay, earthquake. There are two types of earthquake. It is located either if it is on a volcanic origin or a tectonic origin. Okay, volcanic earthquakes are the ones that is happening on a eruption of a volcano or if there is an active system on that volcano. Tectonic, on the other hand, comes from plate boundaries or fault systems. So these tectonic earthquakes is classified either it is interplate or intraplate. Okay? What do I mean by interplate? Interplate meaning it occurs inside the boundary. Okay? Inside the boundary. Intraplate occurs in the interior of that tectonic plate. Okay? Interplate in the boundaries, intraplate on the plate itself. Okay, remember that one. So again, tectonic, it is due to the movement of rocks that is passing from one another along fault lines. And it is when a rock breaks. If that rock will break, waves of energy will be sent out and thus producing seismic waves causing what? Causing earthquake. And it looks like this on this image here. So, say for example, there we have one block system here. This is the pre-stress state. And if there is movement, a slow movement, the whole area becomes uh, drastically deformed. Okay? It is deformed elastically. So, making it that there will be pressure on this portion here. Okay? There will be pressure. Until such, if it is moving slowly and constantly, this area here will be break. So, it will send off what? Send off seismic waves. That will produce what? That will produce earthquakes. Okay. In what way that an area can produce many earthquakes? Okay. We can actually have what? Okay. So I am experiencing earthquake now. At this moment, an earthquake is happening. Okay. So the date is what? Uh, it is a strong one, January 21, 8:25. So while I am pre-recording this, an earthquake has occurred. I don't know. So it is timely. So for a minute. So this is a strong one. I think it has a magnitude of 6 or 5. So our house is moving. Okay? So let me continue. So this one, I am experiencing now an earthquake. That is because of this ruptured structure here. All right? And if we look at this on a larger scale, and if there will be a breakage because it cannot withstand stress, this area here will be what? Will be uh, discarded because there will be no stress here if it has happened that the waves have been occurred. The energy stored has been all going through all throughout the area. But this area here still is being compressed, making it or shear stress. So it has stress and it has stored energy. And eventually, if this area will still move, another earthquake or what we call aftershocks will occur. So we have 1, 2, and 3. This will happen if and only if the area here is still moving, producing what? Almost 3 aftershocks. Because there is still a remaining area that has an energy stored from this whole block section. Okay? So let's look at the 3D version. So this is the fault surface. This area here has been released, but this area here has been released and this portion here has not been released. So therefore, there will become a time that this area here will become will move and eventually it will cause another earthquake. Okay? And earthquakes is based on how the geology of the rocks, the composition of which, because the more rigid the rock is, the more the pressure. And we have, if the area of the rock structure has more pressure on it, the more strong the earthquake is. Okay? So remember that one. Rigidity is very important. The more rigid the rock is, the more strong the earthquake. And if and only if that area has water or has underground water, these water systems, this underground water can actually weaken these faults. Okay? But these faults can eventually heal. It will heal itself and become stronger if minerals are being formed on its section, making it that it will be more rigid, thus producing stronger earthquakes. Okay? And these structures will change over time. Alright? So, what is the principle or the concept of these earthquake systems? Okay? And this is what we call the elastic rebound theory. So again, earthquake is the has the sudden release of stored what? Stored strain and stress in rocks that causes movement along a fault. And this is the theory behind it, the elastic rebound theory. Okay? So if we look at this image here, this is the elastic rebound theory. If I have a a piece of stick, if I deform it from its original position, the stress will be here on its middle portion. And if it ruptures, we can hear something like a crack. And that crack resembles that the strain is being released, meaning the energy is being released, thus producing earthquakes. Okay? So this is the elastic rebound theory. Okay, now, epicenter versus hypocenter. Epicenter is the one that is located above the hypocenter. Epicenter is what? That is located above the hypocenter. Hypocenter is the focus. That is the source of the earthquake that is found below it. Again, the one that's located below is the hypocenter. The one that is above the hypocenter is the epicenter. All right. So next, we have this image here. We have this earthquake here that had happened in Japan. This one here on the star. Okay? And this red structure here resembles the damages. Okay? That the aftermath of this earthquake here. And we can see series of colors. The red ones are scattered all throughout. Okay, question. How is it possible that this area here has what? A lesser damage compared to this area here. And it looks like this coastline is basically in front of the earthquake itself. So this area should have been red all throughout. Okay? So as I've mentioned before, that the rock rigid structure is one factor. So we can determine that this area here has different rock structures. One of which, these red ones here, has the what? The lesser rigid ones. And this yellow, green, and this not so red ones are the what? The lesser rigid one. So this is one factor of an earthquake based on its damages. So these are the factors. So the source, the path, and the site. So the source is if it is related on what parameters on its location and on its fault related parameters. So if it is located below or in the shallow regions or in the deeper regions of the earth's surface. Path on which it depends on the wave that has happened that is going to that direction. Okay? And site is the if it is either amplified or de-amplified. Okay, let's try to look at this image here. All right. So, this is uh, the differentiation between a free surface and a surface that has many structures. So, each of which has its own wave path. And from it, if the rocks, if the wave undergoes soft to hard transition, what will happen? Okay? So making it such that the strength of the wave is being de-amplified. So from stronger to weaker waves as it goes to another boundary. But if it comes from hard, then it will transition to a soft type of rocks. The area is amplified. Thus, the strength of an earthquake will multiply. Okay? Will be stronger than the first wave itself. Alright? So, this explains why softer soil would make an earthquake worse. Okay? The more that the soil of the structure in your house, for example, if an earthquake will happen on your area and your rock structure below is soft, okay, than the areas, uh, let's say on the other barrio, your area will have more damage than that area that has the harder soil. Okay? So with this, we can determine that the red ones has the softer soil structures, and this green, yellow, and not red ones, not so red ones, have the uh, harder soil structures. Okay? So speaking of waves, we have different types of waves. So one is the body wave that is being classified into two waves. We have the P wave or the primary wave. These are the fastest. The orientation or the movement is push and pull, and it travels through rock and fluids. So either solid or fluid types, fluid phases. Shear wave or the S wave is the second wave that is felt in an earthquake that travels only through solid structures, and the movement is perpendicular to the direction of propagation. So let's try to look at this a summary here. So P waves are the fastest. The S wave is slower than this P wave. The P wave is the one that is first to arrive. The second one is the S wave. The P waves can pass through solid and fluid. S wave can pass through solid but not fluid. And P waves looks like this one. The push and pull. Okay? If you have a slinky, the movement of which is push and pull. If you have a rope here that is tied on a structure, if you go like this one, the motion is going on this orientation. So a ocean wave manner. So this is the movement of the P wave. So here you can see that this is moving like a push and pull motion. Okay? On a push and pull motion. The particle is moving on its direction, parallel to its direction. Okay? This is the P wave. The S wave, we have this one. Okay, this is the S wave. The S wave is what? Perpendicular to the propagation. So meaning it has an S wave. It is on a S wave manner. Okay? P wave and S wave. The other type of wave is what we call the surface wave. So these are the waves that travels only along the crust. So primarily the surface of the Earth, the surface of our planet. So it has two classifications. We have the love wave and the Rayleigh wave. The love wave is the fastest surface wave, and it moves side to side. Rayleigh wave rolls along the ground, and most of its shaking is felt, that is that we feel if an earthquake will happen, is the Rayleigh wave, right? So we have love wave. So again, it is moving on a side to side motion. Okay, side to side. The movement of a snake, this is the love wave. Okay, Rayleigh wave looks like this one. Okay, so it is moving, the particle motion is moving on a cycle. So making it the most dangerous wave that is being created or being generated by an earthquake. So again, what are the two types of waves? The body wave and the surface wave. The body wave is being classified into two. The what? Uh, okay, let's try to look at it again. The primary wave or the P wave and the shear wave. The other one is we have what? The surface wave that includes the love wave that is moving side to side like a snake, and the Rayleigh wave that rolls along the ground. Okay? Those are the types of waves. And now we'll try to determine the epicenter of an earthquake. And this will involve at least three seismic stations, because the process here or on how do we determine is that we need to have at least three seismic stations to have triangulation. So here in this image, we have three seismic stations, 1, 2, and 3. And we have the radius and this portion here on which the three circles is being connected or intersected. This is the location of the earthquake or the epicenter. Now, how do we determine this epicenter? Or how do we locate earthquakes? First is that the P and the S waves start out from the hypocenter. Okay, it will start on the source itself. And as they travel, they will separate because each of which has what? Different speeds. Okay? P waves are the one that is moving faster than the S wave. So therefore, the first one to arrive is the P waves. Okay? This P wave here. So from this graph here, the P waves comes first. Okay? The S wave comes second, and the third is the surface waves. Okay, now the interval of time arrival with the between the P and the S wave is basically increasing all throughout as the wave is being the increasing distance of the wave. Okay, so the more that the seismic station is farther than the source, the more that the time arrival of the P and S wave between these two is more than the if the seismic station is nearer than the what? Than the uh, one that's located farther. Okay? And if we can get this distance, the time arrival of between the P and the S wave, we can do it on a map. The time versus distance graph. Okay? So here we can construct earthquake records with the interval with respect with the distance and time of the earthquake itself and from the seismic records. And here, this is the step by step. We have the three stations here, the A, B, and C. So the C is the one that is farther away. B is the second one, the midpoint. And the A is the much nearer from this source. So at the nearer version on the seismogram A, it has a 3-minute interval. Seismogram B, an 8-minute interval. Seismogram C, an 11-minute interval. And each of this interval has its uh, structured distance. So from this 3-minute interval, it has 1,500 distance. 8-minute interval, we have the 5,600 distance. The seismogram C, it has the 8,500 distance. And if we graph these distances here, from its radius, we can determine the portion in the map that has the source of the earthquake. So like this one. As we graph it, because we have the radius of the distance of which it is being recorded by the uh, seismic station. We have 5,600, we have the 1,500, and we have the 8,600. And because of this, we have circles and the portion here that these three stations is being intersected. This is the location of the earthquake. Okay, so this is how you locate earthquake based on the seismic station data, right? So a single station can record only the distance but not the direction. That is why we need to have at least three seismic stations. Okay, and that will determine the hypocenter or epicenter on the uh, earthquake that has happened on that area. And the depth of the focus, okay, the hypocenter, we can actually measure it by the same process. We can classify it by if it is 0 to 70 kilometers, that is shallow. Intermediate, 70 to 350, that is intermediate. And if it is deep, it is 350 and 670 kilometers. Okay? So let's try to have a video so that we will understand more on how do we locate earthquakes.
I'm John Ristow. I'm a seismologist with GNS Science, and I work as part of the GeoNet team. I'm one of the duty seismologists for GeoNet, and so now I'm going to give you a demonstration of how we locate an earthquake, how we calculate the magnitude of it, and how we basically put this information out there for everyone. So this is an example of what an earthquake looks like when we record it. These top 6 traces here are all coming from one station, and when we get an earthquake we get numerous traces that come in from all across the country. This is a animation that's just going to show how we actually record an earthquake. We have an example of 3 seismic stations, and these are linked to the data center by satellite, and this is going to show the traces, the seismic records, as they come in when the earthquake happens. So when the earthquake happens, these 2 different lines are going to represent the P waves, which is the yellow line. It's always the fastest wave, it's always the first one to arrive. And the S waves, which is the orange line. That's always the second wave to arrive. So you can see when we're close to the epicenter of the earthquake, to where the earthquake originated, the P waves and the S waves are very close to one another. As they travel along, the separation between the P and the S waves gets greater and greater. So there's a clear distinction between the P waves and the S waves. We now see the S waves have started to arrive at the second station, and there's a greater time separation between the P and the S wave, so you can tell that the second station is further away from the earthquake than the first station was. And if we continue this along a little further, we now see the P waves starting to come in at the furthest station. And then finally, if we keep the animation going, we now see the S waves arriving at the furthest station. And you can also see the amplitudes of the waves getting less and less with each station, because the seismic energy spreads out the further and further away you get from the epicenter of the earthquake, and therefore the amplitudes get smaller and smaller. Okay, so this animation is going to show how we can actually get the location of the earthquake. So once we have determined how far the earthquake is from a particular station, we can basically draw a circle around the station, because we know how far it is from that station, but we don't know in what direction. And it could be anywhere on that circle. Now if we get that same information from a second station, you can draw a circle around it, and these 2 circles will intersect at 2 points. And so we know that the earthquake has to be located at one of those 2 spots. So if we get that same information then from a third station, we can see that the 3 circles will intersect at only one location, and that's where the earthquake is. Now, in actual practice, there's going to be a little bit of error when you do this on getting the distances from each station, and so these the circles won't nicely overlap at one single point. But if you do this with a number of stations, say 10 or 12 stations, something like that, you can get a very well-defined location for the earthquake within maybe 2 or 3 kilometers. Again, we can extend this to 3 dimensions, so not only can we get the location on the surface, but we can actually tell how deep the earthquake was. So whether it was 5 kilometers deep, 20 kilometers deep, 100 kilometers deep, something like that. The very last step then is to get the magnitude of the earthquake. And the magnitude of the earthquake depends on, again, on the height of these signals that we receive at the different stations. So there's an equation that factors in both the height of the signal, the size of the amplitude of the signal, and the distance from the station. And we can use that, we do that for a number of different stations, and then average the results to get the magnitude of the earthquake.
Okay, so that's how you will determine or locate an earthquake based on 3 seismic stations. Okay, so now, how do we measure earthquake? So there are 2 ways on how do we measure it. One is by magnitude, or the energy release of an earthquake, and the second one is intensity. It is the effect on the site location, or the damage that had happened on that area or location because of that earthquake. So magnitude, okay, it is determined by the Richter scale by Charles F. Richter in 1935. So it is being computed using charts that involves the measuring of the amplitude of the earthquake and the travel time of the S and P. Okay? So, this is if ever that we have the seismic records. So, if we can have the amplitude of this area here and the distance, the P and the S, we can determine the magnitude on that middle. By this structure here, this chart here is what we call a nomogram. Okay? So, magnitude. This is other magnitude scales. We have the surface wave, magnitude, body wave, coda, duration, and etc. So all are based on instrument measurements. And remember that as earthquakes get bigger, the measured quantities do not necessarily increase at the same rate. So we have the nomogram here. So here, this is the amplitude, the 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 highest amplitude, that is the highest record. If we have the 23 mm here, this is the 23 mm here. So the time range of the P and S is 24 seconds. So we have this area here that is 24 seconds. So pinpointing it, so if you have a stick or a ruler, so from here to here, the magnitude is 5. Okay? So magnitude here is 5. This one. So magnitude also is in a logarithmic scale, meaning that a magnitude 5 is 10 times stronger than a magnitude 4. Okay? And based on its energy, or in terms of energy, a magnitude 5 earthquake has 30 times more energy than a magnitude 4. So if we take a reference, okay, a magnitude 8 earthquake is equivalent to a 10,000 atomic bombs that has hit in Hiroshima last time. So with this, we have a table here. This is a scale from magnitude 1 to 4. The energy is in a logarithmic scale. So from 1, it increases to 32, then 1024, and so on and so forth. Okay, magnitude 5 to 8. The energy is exponentially increasing. So the higher the magnitude, the more the energy is being released, the more stronger the earthquake. Okay, we have a graph here. Okay, so these are the series, or the number of earthquakes that had happened on the globe. Okay, so we have the higher the magnitude, the lesser the occurrence. Okay? But we have, if the Earth is actually experiencing low to moderate in a much more higher occurrences. Okay, so I have one video here that resembles the earthquakes, the major earthquakes that had happened all throughout. Okay, so that ends that video. So the magnitude scale is actually until 10, but there was a time that the magnitude is going on the 13th scale. That had happened because there is a impact, an asteroid impact. So that is an external uh, type of body that has happened on our planet. Okay? So with respect to magnitude, this is how we calculate magnitude. If we have the data on the movement of that structure. Okay? So we have the moment magnitude, and the formula we will be using is a two-third log MO, and this MO is the UAD. So this UAD is actually minus 10.7. Then we have here, if it is given, if the data is being given in centimeters, we have the moment magnitude that is log MO over 1.5. And the moment magnitude is UAD. That is, we have the rigid structure that is 3.2 times 10 to the 11 dynes to over centimeter squared. Okay? But the main used formula is this one. Okay? So log 10, 3 times 10 to the 11 times the length, width, and the depth times 10 to the 12 plus 1 times 0.667 minus 10.73. If and only if the length and the width are in kilometers and the depthness is in meters. So the seismic moment, or the MO, resembles the rigid structure or the shear modulus of the crust and the rupture area plus the distance of the movement of the earthquake. So if you have this one, if the data is in the length, the area is in kilometers, and the displacement or the distance of the movement is in meters, and we can use this formula here. Okay, so try to calculate this five uh, earthquake that has happened beforehand. So this has happened before. This is the a real time earthquake data. Okay, just solve this one, just calculate it, and try to search in Google and get the data on what magnitude scale is this happening here, the events here. Okay, now, after the magnitude, we have intensity. So again, the intensity measures on how the area has been damaged. And the most used scale is the modified Mercalli intensity scale. However, we have our own PEIS. Okay, we are using this in the country here in the Philippines. So it is the FIVOX earthquake intensity scale. Okay, let's try to differentiate these two scales. The modified Mercalli is the intensity goes from 1 to 10, and from the shaking if we cannot feel it, and it is on the extreme if everything is being destroyed. The PEIS looks likely the same, but the description is in a general manner. Okay? So the shaking on which comes from the scarcely perceptible, meaning we cannot, if either we feel it or not, and the completely devastating. So each of which events is being designated, or the descriptions of each intensity scale. It is based on the location or the area that uh, that has damage because of that earthquake. So it differs from one city to another or from one province to another. So how do we monitor this earthquake here in our country? So FIVOX has now 101 seismic monitoring stations. And these are the locations of which. So here we can see several seismic stations that is being designated on each of the provinces of here in the Philippines. So it must have again at least three so that we can determine the magnitude of the earthquake, and also the location. But now we have our own technology. Satellites can now actually determine the um, the earthquakes that had happened every now and then. So in monitoring earthquakes, sh- it is enhanced by GPS technology through satellite data. And also the manual type, we have the seismograph that is composed of a seismometer and a seismogram. So again, the instrument is the seismograph. Okay, the whole device is what we call the seismograph. It has two devices. We have seismometer and the seismogram. Seismometer is the instrument itself. It is the recording. Okay, so the recording of which rather is from a seismometer is called the seismograph. That is the paper that traces the earthquake motion. Okay, the accelerometer is the one that measures the ground shaking or the ground motion. Okay, so we have this. This is the seismograph consisting of a timing device, this one, and this one is the recording device, the pen itself. Seismometer is this one. This is the instrument that comprises the whole seismogram itself. Okay? So again, the seismogram is the paper record. The seismometer is the instrument that measures, and the seismograph is the whole device itself. Remember that. Okay? So lastly, we have this information, earthquake information that is being posted by FIVOX so that we can have data on the earthquake that is happening every now and then. So with this, from these infographics, so each of these sections determines the date and time, the location, the depthness of the focus. So remember that if the earthquake happened on a shallow depth, the more devastating it is. The origin, if it is either tectonic or volcanic. And of course, the magnitude. Here on this infographics, this portion here is the reported intensities all throughout the cities or provinces that experience the earthquake. Okay? So this on the lower portion will tell us if we will be expecting damage or not, or if we'll be expecting aftershocks. Okay? So this is how earthquake is being posted so that we can have information. Okay? So this ends the discussion. I hope you have learned something from it. And on next week, we will move on to the next topic, and that topic is all about volcanoes. Thank you for listening and have a nice day.